All right, should we get started here, or are we?
All right, sounds good. So I'm Alan, this is Suyash. Today we're going to be talking about counting and probability.
All right, so let's get started here. So, all right, I'm going to share my screen. Okay, so today we're discussing counting and probability. So here we go. By the way, please let us know if you have questions at any point. So the first kind of subtopic we are going to discuss is counting in sequences. So this appears in lots of places. Sometimes when you're solving a problem, it kind of reduces to counting in sequences. So we want to count the number of elements in sequences, and that's going to help us in a lot of different types of counting problems. So the general strategy to kind of find the number of elements in a sequence is to apply some sort of transformation to it. So for example, if you're going to maybe we say we add 1 to each element, or divide each element by 2. And just by doing this, applying this transformation, it's not going to affect the number of elements that are in that sequence, okay? So yeah, that's an example. So adding 7 to every element of a sequence won't affect the number of elements in that sequence. And then an important theme is finding patterns, which are going to make that counting step easier. So let's take a look at some examples. So how many elements are there in this sequence? Just someone yell it out.
10. 11.
So it's 1, 2, 3, 4, all the way to 10. That's 10 elements, okay? Right, so clearly 10, yeah. This one.
Is there 15 elements in this one?
Sure?
Is there 15 elements in the
And
second
are
one?
you sure?
16 elements. There's 16.
16.
Because 0 is a thing.
Okay, yeah, so that's part of it. But here's the key thing to notice. If we add 6 to each element, right? So notice, -5 plus 6 gets us to 1. -4 plus 6 gets us to 2, all the way to 10. That gets us to 16. That's not going to affect the number of elements that are in it, right? So, I mean, I could give you an extremely trivial example. I have if you add 10 kids and you give them all ice cream, they're still going to be 10 kids. Okay, it's almost that kind of thing. Still the same number of elements. Now from here, 1 through 16, that obviously has 16 elements. So the original list has 16 elements as well. Okay. I know this might seem very basic and trivial, but you'll understand it very soon. How about this one? How many elements would be in that list?
10. 19. Oh, wait, no, 10.
10.
And right, so if you're going to divide all the elements by 2,
10.
so that's another transformation we're applying. You get back to the 1 through 10. So that's an example of, yeah, Alan brings up a good point. So there's this thing called an off by 1 error, which is just what it sounds like. You're off by 1, and often the test designers will often include options that are 1 less or 1 more than the answer. And that can easily trip you up. Like in that previous example with -5 to 10, is oh, well, 10 minus -5, that's 15. So there are 15 elements, right? No, you gotta watch out for that. So, all right, yeah. So y'all understand this?
Yeah.
Any questions?
Yeah.
Okay. All right. Here's another example. So can you kind of figure out, I'll give you a minute to pause and think about this. What transformation could you apply here? And maybe it's multiple transformations that need to be applied. All right, I'm going to give you a few more, about 20 more seconds to think about this one. This is pretty important. good. We got some people getting these answers in. That's pretty good. All right, so let's take a look at how you'd solve this problem. The first thing you do is divide everything by 2. Obviously, negative 40, that becomes negative 20. Negative 38, that becomes negative 19. All the way to 40, that becomes 20. From there, you can add 21 to all elements, and that brings you to the 1, 2, 3, all the way to 41, and we know that has 41 elements. So in kind of examples like this, our main goal is usually to get it to that 1 through n list, and that's going to make it very easy to tell how many elements there are. I mean, you don't have to you could have stopped here if you knew that there were 41 elements from this list, but this is the basic idea. All right, this next one, 1, 4, 9, 15, 25 to 400. How many elements are there in that list? Yes, please only send your answers to me. Yeah, so finding a pattern, that's pretty important. So, okay, this is easier. So you should have noticed that these are all the square numbers. That's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, all the way to 20 squared. So immediately you can probably tell that has 20 elements. And if not, you just take the square root of all the elements. Again, just another one of those transformations. And that's going to give you the list of numbers from 1 to 20. So that has 20 elements. All right, I'm going to turn it over to Alan now.
You're on mute.
Right, sorry about that. So next we're going to be doing a problem from the AMC 10A. How many ways are there to write 2016 as the sum of 2's and 3's? So for instance, 1008 times 2 plus 0 times 3, or 402 times 2 plus 404 times 3, or for instance, 6, or for instance 600, or for instance the 2016 over 3 times 3 plus 2 times 0. Those are just a few of the ways. So just take a couple minutes, try to solve it. Shall we try to go through the solution now, or wait just a few more minutes?
Maybe another like 20, 30 seconds.
Okay.
Guys, maybe try to find a pattern in a clever way here. It's maybe not as obvious as the previous example, but that's really helpful.
All right. So let's start. So we can sort of convert this problem to an equation. 2a plus 3b equals 2016, since there are a2s and b3s. So we're looking for non-negative integer solutions to this equation. So we want to find the number of integer pairs. So that goes from, for instance, 1080, and that goes from 1080 all the way to 0, 672. Right, so we can actually rearrange this equation. Does everybody see how that that comes from it? We subtract 2a from both sides, divide both sides by 3, and we get b in terms of a. The nice thing we can get from this is that we know that 3 is a factor of 2016 minus 2a, and we also have that a is greater than or equal to 0, and 2016 minus 2a over 3 is greater than or equal to 0. So given these constraints on a, we're trying to find the number of integers that work for that. So we have 3 is a divisor of 2016. So since 3 is a divisor of 2016 minus 2a, we'll also have that 3 is a divisor of minus 2a, and therefore a is a multiple of 3. This means that our equation is basically asking for how many multiples of 3 are there from 0 to 1008, since we have, by our second condition, that 2016 minus 2a is greater than or equal to 0. So how many multiples of 3 are there between 0 and 1008? We can use some of the methods that Suyash outlined. So given our list, we can divide both sides by 3 to get this equation, this 0 through 336. And adding 1 to both sides gives us, adding 1 to all elements gives us 1 through 337. That means that there are 337 possible values of a, and therefore 337 choices for a comma b. Any questions about those steps?
Based on the chat, do you want to back up and explain why you have a is a bit less than 1008 and why it suffices to count to multiples of 3? Yeah.
Right, yeah. So
go through this slide again.
We have that 2016 minus 2a is a multiple of 3. So maybe we can express this in terms of the mods that we heard about in the first session. If 2016 minus 2a is a 0 mod 3, we have that negative 2016 is 0 mod 3 as well. So the sum of those is going to be 0 mod 3 as well. That is to say, negative 2a is 0 mod 3. And dividing a multiple of 2, a multiple of 3 by 2 is still going to give a multiple of 3. And as for the constraint of why it's less than 1008, we can basically multiply both sides by 3 to get 2016 minus 2a greater than or equal to 0. Add 2a to both sides to get 2016 is greater than or equal to 2a, and divide both sides by 2 to get 1008 is greater than or equal to a. Do people get that?
Yeah, that makes sense.
Okay. And I also saw a question of why we added 1 to both sides. Well, that's because we can't quite count from 0 to 336 and get 336. The nature of the counting numbers is that we've got to start from 1. So we have to add 1 to all the numbers. Does that make sense? So all right. So anybody got any further questions, or are we ready to continue?
Yeah, that makes sense.
All right. So another technique is multiplication in counting. So to find, sometimes we're not just looking at, we can't just condense everything to one variable, and we have to find the number of ways for 2 different events to happen. And a nice thing about this is that if these 2 events are independent of each other, then you can actually multiply the number of ways of 2 different events happening. But you can't multiply all the time, and it's really important to understand that. So let's take this example. You have 3 options of cake and 4 options of ice cream, and you want 1 cake and 1 ice cream. How many ways are there to do that in total? You can say this out loud.
12.
Nice, yeah. So we can basically multiply 3 by 4, since for every option of cake, there are going to be 4 options for ice cream. And that means that there are 3 times that 4 appears, giving 3 times 4 equals 12. Let's take a more complex example. Here's another AMC10 problem. We have a burger restaurant with 8 options for our condiments. You can choose either 1 patty, 2 patties, or 3 patties, as well as any collection of condiments that you want. So how many kinds of burgers can you have in total? Take a couple minutes for this. And message one of us hosts if you have the answer.
Yeah, Alan, I think I was supposed to go from here, actually. Yeah.
Oh, okay.
Sorry.
You want to share screen?
Take a couple minutes to figure this out.
Wait, didn't we just go over this? Like this problem?
You took.
Oh,
you
sorry,
got
I'm
me
on the wrong problem. Yeah,
Yeah.
let me. No, I don't know. So, this is the problem we want. So first, you need to figure out how many ways you can choose a collection of condiments. So, think about this. You have 8 options for condiments, and for each condiment, you can either include it or not include it. That's 2 options. So, how many ways do you think you can choose condiments? Either just say it out loud or drop it in the chat. So once again, we're just looking at the condiments here. You have 8 different options. You can have as many as you want. So for each condiment, you either include it or don't include it. That's 2 different options. And you have to make that decision 8 times. So remember, each condiment is independent of whether or not you choose the other ones. So it's going to be 2 times 2 times 2 times 2, 8 times. So 2 to the power of 8. Okay? So that's actually yes, you can have 0 condiments. So there are no restrictions with that. So yes, 0 condiments is definitely an option. Yeah, 2 to the 8th, that's 256. Okay? So there are 256 different ways that you can choose condiments. And yeah, so someone, okay, that's, we haven't quite gotten there yet, but someone said that, like, if you know combinatorics, that's 8 choose 0 plus 8 choose 1 plus 8 choose 2, because you can either have 0, 1, 2, all the way to 8. And that's going to be 256. So if you remember, so yeah, if you, actually, I won't get into that right now. But the point is, you have 2 to the 8th, 256 ways to choose condiments. Any questions about that part alone? Okay, and just to illustrate this point better, if you have, let's say, only 3 condiments, you could have no condiments, condiment A, B, C, condiments A and B, A and C, or B and C, or all 3 of them. And you can see there are 8 possibilities. That's equal to 2 cubed. Any questions so far? All right, well now, you have these 3 options for patties. You can have 1 patty, 2 patty, or 3 patties. That's 3 different options there. So what are we going to do next? Someone tell me.
Multiply by 3.
Okay, good. So 256 times 3 options for condiments, 3 times 2 to the 8th. So that's 768. So yeah, we don't have that here, but yeah. Any questions about that problem? None? All right. Yes, please do ask questions at any time. Otherwise, we don't really know kind of what you might be struggling with. Or
yes, somebody was asking in the chat, how do we know we can multiply the 2's?
Well, anytime they're independent, you can do that. So, because no matter what condiments you choose, you still have that option of 1, 2, or 3 patties. So for each selection of condiments, there are 3 different options for the number of, for each of these condiments. 256 options. There are 3 options for the patties. So you just multiply those 256 by 3. Does that clear things up?
Or, yeah, I think the question is how we can multiply the 2's to even get to 2 to the 8th before the 3.
Oh, because for each condiment, you have the option of adding it or not adding it.
Yeah, so it's important not to think of them as a whole, but to think of them one condiment at a time. Don't think like 0 condiments or 1 condiment or 2 condiments or 3 condiments. You can instead think about it as mustard or no mustard. That's 2 options. Then multiply that by ketchup or not ketchup, mayonnaise or not mayonnaise, and so on and so forth for every condiment.
So that's that. Okay. Yeah, so 3 times 2 to the 8th, that's 768. Okay, now the next major topic of today, it's probability. So I'm sure you all have at least had some experience with probability. So for any event, suppose that there are n possible outcomes, and suppose any of these outcomes are good, or the probability that it happens. Okay, well, then the probability of a randomly chose outcome is m over n. Let's see, what do we have in chat? All right, so note that this is randomly chosen. So that assumes that each outcome is equally likely to occur. So let's say you flip a coin. You can get, let's assume that it either lands heads or tails, and it's equally likely to land both. What is the probability that it lands on heads?
50%.
Okay, so yeah, 50% is correct, but we usually express probability as a fraction between 0 and 1. So that would be 1/2 in this case.
So
Because-
0.5.
Yeah, so 50% is the same as 1/2. Now, let's say okay, here's another example. Let's say you're rolling a dice, you're rolling a die, and you win a prize if you get either a 5 or a 6. So what is the probability that you win?
1/3.
Okay, so yeah, there are 6 possible outcomes, and 2 of them are good. So the probability is 2 over 6. Now we write probabilities as fractions, and just like fractions, we can simplify them. So 2 over 6, that's going to simplify to 1/3. All right? So, yeah, so this is just an example of one good outcome. It's 1/6. Yeah, probability of a good outcome occurring equals number of good outcomes over number of total outcomes. This will be very important. Now the concept of multiplying and adding probabilities. Let's see. So if we have 2 independent events, and independent is a very important concept, and the probability of both those events occurring concurrently at the same time is the probability of that first event occurring times the probability of that second event occurring. So let's like think of an example. So let's say you have your 2 favorite sports teams, maybe a football and a basketball team, and they're both playing today, and you want to know the probability that they both win. Let's assume that whether one team wins doesn't affect the probability that the other team wins. Then let's say your first team has a 60% chance of winning, or 3/5, I should say. 60%, 3/5, same thing. And your other team has a 1/2 chance of winning. Well, then the probability of them both winning is 3/5 times 1/2. That's 3/10, okay? Now, of course, they have to be independent. So let's say the probability of one team winning affects the probability of the other team winning. Or for example, let's say you really like the Lakers and the Warriors. But today the Lakers are playing the Warriors. Well, obviously they can't both win, because if Lakers win, then the Warriors lose and vice versa. So they have to be independent. All right, here's an example. You roll 2 dice. What is the probability that the first dice is a 4 and the second dice is a 3? Just think about this.
1/36.
Okay, yeah. So this is there we go. So the probability of the first dice rolling a 4 is 1/6, and the probability of the second dice rolling a 3 is 1/6. Now, since those are independent, the probability of them both happening is 1/6 times 1/6 is 1/36. Now, okay, so this is kind of confusing how this is written. Now, event 1 and event 2 to happen, you multiply the probabilities. When you want event 1 or event 2 to happen, well, that's kind of confusing. So what is true is if you roll 1 die, then yeah, the probability of getting a 3 and a 4 is 1/6 plus 1/6 is 1/3. Now that's because they can't happen concurrently. So if you want to know the probability, so if they can't both happen at the same time, then yeah, you can just add them. But there's also, if you want like,
It's also
if you wanted the
important.
probability that you get a 3 or a 4 on both dice, that becomes a little more complicated. Because you then have to take into account, I was like, oh, what if it both, or whether, okay, let's think about this question.
So
Let's say, or how about this?
one-
Let's say you roll 2 dice and you want the probability that either the first one gets a 3 or the other one gets a 4. That's a bit more complicated. Because then you have the possibility that they can both happen together. So that's important. So I think we might get into that sometime later, but that's not the focus of today. Fine, I'll
All
turn it over to
right.
you, Alan.
All right, I'll take it over from here. So let's see. Our first problem is we have a radio program with a quiz of 3 multiple choice questions. Each question has 3 choices, and your contestant wins if they get 2 or more questions right. The contestant isn't very smart. They just answer randomly to each question. So what's their probability of winning it? Take a few minutes, try to solve this.
Yeah, this is one of those important problems that kind of sums up everything in this section. You have to consider all the cases. This is one of those cases where you add probabilities because, remember, these can't occur together. Either you get 2 of them right, you get 3 of them right. You can't have them both happen at the same time.
Yeah,
But to find the probability of getting a question right.
But you're
need to
gonna have
multiply
to
them.
do some multiplication as well.
That's right. And remember, the contestant wins if they get all 3 right as well. So that's something else you have to consider. Is anyone still working on this?
When it says probability, like what match should we do? Like how should we do it?
What do you mean by that?
Like for what steps should you take for that, or like
And try
Well, that's
to
what you have to
find
figure out. So you kind of need to
Try
figure out the
to
best way.
try to find each case of this case in which the contestant wins and try to find the probability
Yeah, so
of each
case
case.
work. So that's another important concept in probability. Sometimes you need to divide it into cases. So in this case, in this problem, you need to divide it into cases where they get 2 questions right or they get all 3 questions right. And then in the end, you can add up the probabilities together.
So for the probability, what should the answer be in? Like, should it be in a fraction or should it just be in
A
a whole?
fraction.
So yeah, fraction. So on a math competition, unless you're told otherwise, you'll want to write all probabilities as fractions. Sometimes decimal, but more often than not fractions.
Okay.
All right, I think we should start going over the solution now.
All right, so let's say we have a grader for this this radio program, and they mark the answers with zeros and ones. If the contestant gets it right, it's a 1. If it's a 0, it's wrong. So if they answered Q1 right and Q2 and Q3 wrong, that list would be 1, 0, 0. So the number of questions answered correctly is the number of ones. So we want at least 2 ones on the list. And there are going to be 4 cases for this. 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. Did that make sense to everybody?
Remember, a 1 is when you get a question right, so you need at least 2 ones to win.
Right, yeah.
Oh, I understood a little bit.
Oh, what part did you not understand?
I said I understood a little bit.
Okay, so is there something you didn't understand, or are you?
First, I was confused about like what the 1, 1, 0 means, but now.
Yeah, the 1s are for questions answered correctly, and 0s are for questions answered incorrectly. So obviously you need at least 2 ones to win.
Yeah.
All right, so now we'd like to find the probability that each one of these cases happens. Now remember that the answers on each question are going to be the probabilities of answering each question a particular way are going to be independent, which means that we can multiply them. So the probability we get a question is incorrect is 1/3, and the probability that you get it wrong is 2/3. So if you answer questions 1 and 2 correctly and question 3 incorrectly, the probability there is going to be 1/3 times 1/3 times 2/3. Similarly, for 1, 0, 1, it's 1/3 times 2/3 times 1/3. And 0, 1, 1 is going to be 2/3. 1 is going to be 1/3. Sorry, the probability of 0, 1, 1 is going to be 2/3 times 1/3 times 1/3. Sorry about the typo there. It's supposed to be 0, 1, 1. Finally, our probability of 1/3 times of 1, 1, 1, all questions correct, is 1/3 times 1/3 times 1/3. Since we need to get all of them correct. Do you all follow that, or?
Some people are asking in the chat, can you explain
Yeah.
why you multiply the probabilities?
Okay.
And the subsequent places.
So I suppose it's because of that and. We want both to happen. So it's you could sort of think of it as let's say that the probability that let's take this 1, 1, 1. The probability that you answer the first question correct is 1/3. And in that specific case, the in that specific scenario, the probability that you answer the second question correctly is one third of one third, or one third times one third, 1/9. And in that case, in that scenario, the probability that you get the last question correct is one third of those scenarios. So that's going to be one third of 1/9, one third times 1/9. Does that make sense?
Yeah, and somebody asked me in chat, why did you have a 2/3 in the first three cases?
It's because we had that 0, the incorrect answer. And since a correct answer has a probability of 1/3, an incorrect answer has a probability of 2/3. Now all we need to do is say the probability of any of these situations happening is going to be the sum of all the cases. So we just add everything up. 2/27 plus 2/27 plus 2/27 plus 1/27 is 7/27 in total.
Something I want to add here. So some people in their solutions, they just said, well, either he gets 2 right or you get 3 right. If you get all 3 right, then it's, yeah, 1/3 times 1/3 times 1/3, 1/27. For getting 2 right, though, there are 3 ways you can do it, right? You can either get 1 and 2 right, 2 and 3 right, or 1 and 3 right. Now, the probabilities of all these happening are equal, right? I mean, the probability of getting 1 and 2 correct and 3 wrong shouldn't be any different than the probability of getting 2 and 3 correct and 1 wrong. So they just said, okay, well, 1/3 times 1/3 times 2/3, right? Because that's the probability of getting 2 right. But then you multiply that by 3 for the number of ways you can get 2 right. Does that make sense? That's just kind of a shortcut some people took. And you can see these are all equal, 1/3 times 1/3 times 2/3, 2/27ths. And the next 2 terms in that are all the same thing.
All right, if nobody has further questions, then we'll proceed to this last question. 4 fair 6-sided dice are rolled. What's the probability that at least 3 of those 4 dice show the same value? Now, this problem is going to be a little more difficult than the last one, so it's all right if you take a bit more time.
By the way, someone's asking on the previous question.
Yeah.
Why are 1/0/1 and 1/1/1? Why don't they have the same probability? Why can't you just say, oh, half the scenarios have 2?
Because, so yeah, for that question, 1/0/1, so a 0, the probability of getting it wrong, there's a 2/3 chance that you get it wrong, but only 1/3 that you get it right. So the 1/0/1 is actually going to be twice as likely.
Yeah, basically.
Alan, they can see what you're doing. Just FYI.
Sorry.
So for next week, counting probability like 2, is it going to be the same thing but like a little more practice?
There will probably be some new concepts. Actually, let me check. I don't know if this is actually. Let me take a look. So yeah, we are continuing with counting and probability next week. There will be some new concepts next week, probably like more casework and all that, and some harder counting and probability problems. Yeah.
Oh, okay.
Okay, I've only had one person send me the right answer so far, so keep thinking about this one if you have time. I think slowly some people are starting to get it, but I think we may want to start going over the solution. This is a pretty challenging one, but
All right, sounds good. So we're going to have two cases for this problem. First case is where all the dice come up the same. And the second case is that one die comes up different from all the others. So we're going to add these two cases to each other at the end. And in case one, no matter what the first die is rolled, for instance, if the first roll is a 3, then there's a 1/6 chance of the second one also being a 3. There's a 1/6 chance of the next one further being a 3. And there's also a 1/6 chance of the last one further being a 3. So you have a 1/6 cubed, or 1 in 216 chance of rolling all of those dice with the same number. So in case 2, this is going to be a bit more complicated, because remember that there are going to be 4 cases for the die that's different. So you could have 4, 4, 3, 4, but you could also have 4, 4, 4, 3, or 3, 4, 4, 4. So we have 6 ways to choose the value of the die roll that the 3 of the dice show, and
Wait, shouldn't
5
case 1 be 1 by 6 power 4? There are 4 dice.
not
Wait, are there 4 dice or 3 dice?
yes,
There
there
are
are
4
4
dice.
dice, but remember that in addition to 1, 1, 1, 1,
Oh yeah, okay.
there's 2, 2, 2, 2, and so on.
Another way to think about it is that there's 6 possible good cases where you
Yeah.
roll all 1s, all 2s, all 3s, all 4s, all 5s, or all 6s, and then you divide that by 6 to the 4th. So it's 6 over
Yeah.
6 to the 4th, which is 1.
Right, yeah. So there are 6 ways to choose the dice roll that 3 dice show. In which case you only have 5 ways to pick that odd one out. And there are also going to be 4 ways to choose the die that's different. So we have 6 times 5 times 4, all out of 6 to the 4th. And that's going to be our number for case 2. And do people follow that? Oh yeah, another way to do this one is that there are 4 different ways to organize these. Then there's going to be then if you pick one of these conforming dice, there's going to be a 1 in 6 chance that each of these 2 are the same, and a 5/6 chance that that one is different, giving you 1/6 times 1/6 times 5/6 times 4 chance of getting this particular case. So we therefore get a total probability of 1 in 6 to the 3rd plus 6 times 5 times 4 over 6 to the 4th. That's going to be 126 over 6 to the 4th, or 7 over 72. And that's our answer.
Somebody's asking why you multiplied by 4 in the second case, and if you could go over what case 1 and case 2 are again, and why those are going.
Sure. Yeah. Case 1 is when all the dice come up the same, and case 2 is when one die comes up different from the others. The reason why we multiply by 4 is that for every case in which, for instance, die number 1 comes up a 3, and all the other dice come up a 4. There's another case where die number 2 comes up a 3 and all the others come up a 4, or when die 3 comes up a 3 and all the others come up a 4. So we're multiplying by 4 because of that fourfold symmetry almost in the cases. Does that make sense?
So the basic idea for case 2 is that kind of the two cases, right? So one is when all the dice come up the same because we want at least 3 to be the same. And the other one is when one die, you have 3 dice that are the same and 1 dice that's different. So first of all, you have 4 ways to choose which die is the different one. So it could be the first one, second one, third one, fourth one. And then you have to choose kind of actually what value that is. So for example, if 3 of them were a 1, then the fourth one could be a 2, 3, 4, 5, or 6. So that's where the factor of 5 comes in. The factor of 4 comes in because there are 4 different dice, which could be that different one. And that factor of 6 comes in because it could be any of the 6 numbers, 1 through 6, that could be that one that appears on 3 of the dice. But for the first case, the only extra factor that you get is a 6, because there are six ways that you could choose to cover all 4 die. That's why it's actually 6 over 6 to the 4, 1 over 6 cubed.
Isn't this question a little bit similar, like the question before?
Yes,
The
it
regular
is.
one?
Yeah, similar concept with these cases. But yeah, I think the math for case 2 here is a bit more complicated.
Any other questions?
Yeah, so if nobody has any more questions, I'll just go over a bit of logistics, if that's okay.
All right.
All right, yeah, so thank you, Alan and Suyash. Yeah, thank you everybody for attending. Our next class is going to be next week at the same time. Yeah, our handout has been uploaded before the class, so next time we're also going to upload the handout before the classes for each subsequent class. So that way, if you're confused during the class, you can refer to the handout to back up or look at walkthroughs, just in case we were going a little too fast. And yeah, we're going to upload the recording soon for the class, and there are extra practice problems that you can review, as well as you can review the walkthroughs in the handout. Again, that's been uploaded to the website. And yeah, please feel free to ask questions to us by email if you're stuck on anything. And yeah, next class will be next week, like we said. So is there anything else, Alan, Suyash?
Don't think so.
So yeah, handout has been uploaded. You'll get an email when we upload the recording, and when we upload next week's handout with the reminder. All right. If there's nothing else, thank you everybody for attending, and we'll see you next week.
Bye, everybody.
Bye.
Bye.
Thank you. Bye.
Thank you. Bye.
Thank you.
Thank you. Bye.
Thank you. Bye.
Thank you, Suki. All right. See you, Alan.
Bye.